extra bond to the aluminum. And that's why I said it actually behaves more like this one, where you would actually have the aluminum coming by and coordinating, where it would look kind of like but I think it's simpler to just show it like that. So that's ACO substitution, where you stop after the addition of one hydride. So all of this stuff you can add to your list of ways to make alcohols, right? Okay, and y'all have a list, right? Okay. And this is a way to make an aldehyde. But don't worry, if you forget and you treat this with sodium borohydride or lithium aluminum hydride, what would that product look like?
OH. That's because this one has only one hydrogen?
That's right.
All right.
So lithium aluminum hydride, sodium borohydride gives you that. So can we still get to that from that?
If you have excess?
No, I mean just in a second reaction.
No.
H2?
Isn't it ZN BCC?
PCC? Yeah? No?
So from here to here.
Yeah.
Oh,
If you're going the other way, yeah, I mean you can use sodium borohydride to make it, right?
yes, that's why I said in excess, maybe.
Yeah, so if you take the, it's this stuff, right? So you go all the way to the alcohol. Sure, you could go all the way to the alcohol and then reoxidize it back to the aldehyde. That's perfectly fine, right? So all is not lost if you know the oxidation of alcohol. But you can do it in one step and it takes less time and it's better. All right, y'all with that? Okay, so the next one is the reduction of amides using lithium aluminum hydride. So is nitrogen a good leaving group? As N minus? No, right? N minus is one of the strongest bases we use, right? Okay, so nitrogen, hydrogen have pKa's of like 35, right? So they're very, very not acidic as the conjugate acid of nitrogen as a base, right? So they are not good leaving group at all, okay? So much so that when you do this, the nitrogen does not leave at all, okay? So the nitrogen in fact stays, and during the course of this process makes the oxygen go away, okay? So what you get from these are amines. So you can make primary amines, secondary amines, or tertiary amines, depending on what is attached on the other side of the nitrogen. Okay. So how does this work? Okay, so I won't ask you the mechanism for this. So if you want to just watch and not even copy it down, that's fine. You got that on tape?
Yeah.
No mechanism for this one. Does anybody say on tape anymore? Can I see it? Are you recording this? Is that better? Anyway, so just like the rest of them, you're going to add the hydride H minus, I'll abbreviate it in this case, to here, and get, I'll go down this one. This, okay? So, after doing this, when you have the O minus, like I said, the nitrogen is too poor of a leaving group for this to kick back down and push it out, okay? So you're sort of locked in at that alkoxide, okay? So if you're thinking in this kind of way, right, you don't have a neutral oxygen, but a negative that's gonna be very attracted to that Lewis acid, okay? So in this case, instead of making it O minus, it's gonna be O, aluminum, like such, okay? And the relationship between oxygen and aluminum is a very strong sort of bond, okay? So they're very content to sort of be with each other and kind of go away as a pair, okay? So what ultimately happens here is that this will push down and make the oxygen go away. Okay? So the reason why I don't have you guys show this mechanism is it gets a little bit weird in where the charges are, and it's a little more involved than what I want you guys to really keep track of. So our general rules of, if you're using lithium aluminum hydride, we're basic conditions, right? So really only negative and neutral should be allowed. Okay? You do this and kick out, you form a nitrogen plus, okay? Which is very, very short-lived because you also don't want this negative next door to a negative, right? I mean, that's not gonna happen. So ultimately, during the sort of transition of this process, another H minus gets delivered here to neutralize everything. So the key to this though is to realize that the nitrogen is sort of the dominant entity, and it's gonna push out this group rather than allowing itself to get kicked out, okay? And ultimately, you do this and you get to the end.
Is that H minus gonna come from there?
Yeah, it would come from another,
Okay.
yeah. So maybe it's even okay to show it like that. Because it probably happens sort of in a cyclical kind of like, as it's pushing down and kicking out, the hydride's coming in.
Okay.
A little more concerted than what I showed it. So what I really want you guys to realize here is that this is another way to get rid of a C double bond O. Okay? What are the other two ways you guys know?
Yeah.
To get rid of a C double bond O completely?
The H2 and H2.
Wolff-Kishner.
Or
Or
ZN.
the zinc mercury
Yeah.
Clemens introduction, right? So what you don't want to do is treat an amide with one of those conditions, okay? Because other stuff can start to happen, all right? So if you want to get rid of the C double bond O and make an amine, lithium aluminum hydride is your thing, okay? Questions about any of that? Good? All right. let's look at the R minus stuff. So R minus is adding an R group, right? So this is dealing with the organometallics stuff. So Grignard reagents, the Gilman reagents, organolithiums, those guys, right? So the mechanisms of these are going to behave exactly the same way, okay? Only you're delivering that R entity rather than a hydride, okay? So it's going to be the bond between the metal and the R group that's going to be doing the work, okay? So the key with these is you got to make sure you count your carbons, right? Because a lot of times people will mess this up by not including this carbon or accidentally adding another one, okay? So if your Grignard reagent has 1, 2, 3, 4, 5 carbons on it, you better be adding 5 carbons to this, okay? So at the end of the day, if you start with an aldehyde, you make a secondary alcohol, 1, 2, 3, 4, 5, with however many carbons added, okay? And your Grignards or lithiums can be single bonded or double bonded, and that's fine, okay? You're not really forming a triple bond with a metal on it. If you have a terminal acetylene, right, or terminal alkyne, you can deprotonate it and make it a nucleophile that way, okay? And we've done that before. So what did I forget here? Well, the magnesium is just going to sort of go away at the end of the day.
What about Cl? Chlorine?
It will be with the magnesium salt and get washed away with the aqueous workup. So what about the product that I mess up? Right? For the same reason as the hydride stuff, you start with a trigonal planar thing, the Grignard can come in from either face. Okay? So you get that racemic mixture. All right, so mechanism for this, I'll just use it from up here. The bond between the metal and the group that's being added goes and attacks the carbonyl-carbon, kick up the electrons, nucleophilic addition style. Protonate the alkoxide, done.
Don't you put the wiggle line beforehand already?
You can, yeah.
Okay.
Most of the time, if I'm doing a mechanism problem, I'm going to give you one that's not chiral. But the mechanism is the same regardless of if you get a chiral center or not. Everybody okay with that? And so again, HCl is the workup, okay? And typically HCl is going to be aqueous anyway. So you can use water or acid. We will do a Grignard reaction where I think we use something like 3 molar HCl, which is just aqueous HCl. It's just a little better proton source. But if you put in just water, that's fine, okay? All right. What do you suppose will happen if we treat the acid chloride with another organometallic reagent? So if you follow sort of the mechanism, okay, you're going to draw in the bond here. You're going to come in, kick up the electrons, just like always. O minus, Cl,